y distance away from this neutral axis. So what will be this area? And if this is dA and this height is dy, elemental height is dy, and the total area is dA. Now dA is the area of this elemental strip. What is the definition of B? B is width of beam section at EF level. If you can see in your notebook, last time when we have done for the rectangular section, we didn't have to think about the B because, yes, please mute yourself. So the B was the same for the entire height of the rectangular part. So we were not even bothered that where we will consider the B. But here we have to think about that because here the width which is at the EF level is not the same for the entire beam section. It will vary from neutral axis to the top. So that's why the definition of B in this expression, you have to remember that this is the width of the beam section at this EF level. Now this is the elemental strip we have considered at the EF level because this is also y distance away, this is also y distance away, whose area was dA and the height was dy. So what will be the area dA? B, that is the width of this elemental strip or the beam section at EF level into dy, that is the area. Now but do we have any information about B? No, we do not know what is the value of B as of now. So what the things we know? We know from this expression and this given thing, we know the radius r that is given and the y distance which we have assumed as the distance between neutral axis and EF layer. So our motto will be to replace the value of B in terms of R and Y because this one is given to us and another we have assumed, but B we have to replace in this expression. So our motto will be to find out the replacement of B in terms of R and Y. How we can do that? See, this is a radius as well at any point from the center. So this is R. Okay. Now, this is the perpendicular distance from this neutral axis. That means if we again draw this radius here and this is a perpendicular, this length will be equals to this length from the symmetry of these triangles. And if this is perpendicular, as both the this is also R, so this distance from E, say the point is B. So basically EB is equals to BF, or EB is equals to half of EF, as EF is the total distance. Now, what is EF? EF is basically B, because B is the width of beam section at EF level. So EF is basically B. Now EB is half of B. So B is 2EB. Now, how we can find out this EB? What will be EB? Anyone?
Using Pythagoras theorem.
Yes. So, can you tell me the expression?
R square minus y square root.
Yes. R square minus y square, square root of this R square minus y square. That means B will be 2 into this part. So now we can replace this B with respect to this R and Y, and then eventually we can find out this dA part. So let me go back to the next part. So B is basically 2 into root over R square minus Y square, and dA is equals to B into dy. That means 2 into R square minus Y square dy. So this is the elemental strip area which we have found out in terms of R and Y. Now, AY dash is basically integration of y dA. Where it is coming from? If you for to find out the centroidal distance from one axis, what is the process? Integration y dA by A. So this AY dash is basically, if we just keep this A from this here to here, is nothing but y into dA, that's integration. So AY dash will be integration of y dA equals to dA already we have found out. So 2y integration of R square minus Y square dy. What will be the integration of this part? Acha, before that, what will be the two values from where this portion will vary? From the figure, what will be the two values of this integration, the limit of the integration that we can use for this part? Can anyone tell from the figure?
Y to R.
Good, very good. So why y to r? Let me explain for others. Because we are trying to find out this area. We are trying to find out this area, right? This area means not the outside, the distance between this part. Now, this is the neutral axis. So from here, one distance is, just 1 minute. One distance is R, because that is the topmost here, and the area you are starting from this y point, because the expression for shear stress is basically the area above this EF level, and the area varies from y to r. So we will keep the limits of the integration from y to r. So here we will use y to r, here also y to r. Now you can tell me the integration of this part.
So 2 by 3 into r square minus y square whole to power 3 by 2.
Good. That's it.
Yes, sir.
माइनस नहीं आएगा.
Sir, by putting limits.
अच्छा, तुम उसका बीच वाला बोल रहे थे. Okay, yes. So what I am trying to say, so basically this can be done like this. So if you take this minus here and this minus 2y and r square minus y square di y r, and this is basically an integration of, or rather this is the derivation, so r square minus y square whole to the power 3 by 2 by, here it will be 3 and here it will be 2. Yeah, so 2 by 3 r square minus y square whole to the power 3 by 2. Just 1 minute away. হ্যাঁ শুভদীপ বলো, আমি ক্লাসে আছি, আমি. ও আচ্ছা, হ্যাঁ ঠিক আছে, পরে কথা বলছি. হ্যাঁ, ওকে. Okay, so 2 by 3 into r square minus y square whole to the power 3 by 2. Then this, is it coming for everyone? Because that's why the minus I am telling, because this minus is important, because when you will put the values, then this minus will be consumed. Okay, so if you now put these limits, what will be the final part? This r, if you put as y, that will become 0 and y will give us the y, but during that case the minus will consumed up. So finally we have so this ay bar is basically equals to 2/3 of r square minus y square whole to the power 3 by 2. So a y dash y bar equals to 2/3 r square minus y square whole to the power 3 by 2. Now what is our shear stress distribution? The formula S A y bar by IB. So we are replacing here S 2 by 3 r square minus y square whole to the power 3 by 2 by IB. So now what is the B? B is nothing but 2 into this EB. That means is 2/3 r square minus y square 3/2 I into r square minus y square to the power half. So is that correct? No, I have to put on 2. Yeah, because 2 into square root of r square minus y square. So that is coming. So these 2 gets cancelled. This one is only r square minus y square will remain. So basically is by 3i r square minus y square whole to the power will be nothing. So s by 3i whole into r square minus y square. Just 1 minute, one monkey has come. Okay. Okay. So s by 3i into r square minus y square. So that is the shear stress expression for circular part, and from this quadratic function of y, again we can see the distribution will follow a parabolic curve. So now what will be the tau values along the beam section height? So this was the beam section. This is our NA. This is the radius R. We want to draw the shear stress distribution along this height. What was the formula? Tau equals to S by 3i into r square minus y square. Okay. So what will be the value of y at NA?
y0 है सर.
y0 रहेगा. That means tau will be s by 3i r square. Okay. And what is the value of this y at this extreme point, at this top level?
R.
Yes, R. So top and bottom, because here also y becomes R. So tau will be 0. So from this expression, we are getting that as the y value increases, the shear stress is decreasing. तो यहाँ पे y अगर 0 हो गया, that means this is giving us the maximum value of the shear stress. So this is nothing but tau max. Now, and this is the tau minimum, because here the y value is maximum and we are putting it here, that's why it is giving us the tau minimum. Now, what is the I? I is the moment of inertia of the beam section about NA. Right? So, what will be the I? What will be the I for this circular beam section?
Pi R4 divided by 4.
Pi R4 divided by 4. So S R square by 3 into pi r to the power 4 by 4. So that means equals to 4/3, this one. 4/3 S by pi r square. So this is the tau max. 4 by 3 into S by pi r square. So this is the maximum value happening at Na. The values at the top and the bottom is 0, minimum. And this will be a parabolic expression because this is a parabolic curve because it is having a quadratic expression. So this is the shear stress distribution for circular cross section or circular shaped beam section. Here it will be simply the Y part. Now last time for the rectangular part we have shown the relationship between the tau max and the tau average. So if we want to do the same here as well, so what will be the relation? So tau average is basically what is the shear force average, the shear force acting at the section by area of the section. The shear force acting at the section is S. What is the area of the section for circular? What is the area of the section of a circular section of radius r?
Pi r square.
Pi r square, yeah. So S by pi r square. Tau max is 4/3 of S by pi r square. That means 4/3 tau average. So tau max is equals to 4/3 of tau average. This is for circular. What was the relationship between tau max and tau average for rectangular?
Sir, tau max 3/2 of tau average.
Tau average. So that's why I told that in the last class also that this is not unique or this is not universal. This varies with the type of shape of the beam section we use. So, but for numerical purpose, you can remember. So rectangular section, tau max is equals to 3/2 of tau average, and circular is tau max equals to 4/3 of tau average. Okay, so this is the common relationship for circular and rectangular portions, which are the most used beam sections. So we have done the part, and both the cases we have drawn the shear stress distributions as well. and both the cases we have seen that it is going with the parabolic nature because the quadratic function is there. So now we are going for the next type of shape, which is little difficult as compared to this one, but we will solve it. Is an I section. It's a symmetrical I section who's having, okay, first before going for that part, let me tell you the definition. So a I section is basically is having three components, where the upside, this is called flange, this is basically top flange, this is basically bottom flange, but in a way we can denote it as flange, and this portion is known as web. Okay, so we will name this part and simultaneously we will go through like this. So this is flange, the top portions and the bottom portion, horizontal ones, and in between that is known as web. So what is the dimensions we will use? Say this is B, the width of the flange outside. Inside of that width of the web is small b. This height of the web is small d. And this is capital D is the height between the top flange and the bottom flange. So this is the dimensions. Please draw this part and we will try to find out the shear stress distribution for this I shape. So what will be the first step?
न्यूट्रल एक्सिस डिफाइन करेंगे.
न्यूट्रल एक्सिस कहाँ पे जाएगा इसके लिए, सिमेट्रिकल बाइसेक्शन के लिए? न्यूट्रल एक्सिस एक्चुअली कौन सा एक्सिस को डिफाइन करते हैं फॉर ए सिमेट्रिकल सेक्शन, और इट्स नॉट फॉर ए सिमेट्रिकल सेक्शन? डेफिनेशन याद है जो डेफिनेशंस पे बोला था कि न्यूट्रल एक्सिस शुड कोइंसाइड विद समथिंग? याद है वो
Center of gravity.
Centroidal axis. Yeah, that's good. Okay. So neutral axis coincides with centroidal axis. Remember this part because अभी तक जो हम लोग किया दैट इज ऑटोमेटिकली हमारे दिमाग में आ जाता है कि बीच से जाएगा, लाइक फॉर सर्कल, लाइक फॉर रेक्टेंगुलर. यार सिमेट्री में तो until and unless we are dealing with symmetrical, there is no harm because automatically we can find out the neutral axis passes through this mid portion here. But when there is some unsymmetrical sections, so we have to find out the centroidal axis there first, and then we will consider that centroidal axis as the neutral axis for the entire part. And unless or until you are not getting the neutral axis correctly, your all answers will be wrong. So for any sections, if it is unsymmetrical, you have to find out the centroidal axis first, or the position of the centroid first, then the axis which is passing through that centroid will be your neutral axis. Okay, but here it's fine because we understand that this is a symmetrical eye section. So here, because this is B, means this is also B. I have not written it here. Okay, so this portion is also B. The height of this flange, top flange, is same as the height of this bottom flange. Everything remains same. It's a symmetrical section. So for this part, the neutral axis will coincide with the centroidal axis, and the centroidal axis will pass through the mid portion here. So that will be our neutral axis. So for this case, we will divide the job in two parts. As Acha, before that, let me show you one thing. So this is the shear stress distribution, this is the shear stress formula. S is what? The shear force acting on the section. A, Y bar, I, B. What is this? All these components are dimensional properties, means they can be calculated if we know the dimensions of the beam section. Area we can calculate if we know the dimensions. Y bar we can calculate if we know the dimensions, because dimensions से हम लोग को पता चलेगा कि centroid कहाँ पे होगा, and centroid से पता चलेगा neutral axis, neutral axis से पता चलेगा what will be the Y bar. I is, again we know, it's a dimensional property, and B is obviously a dimension. So except this S, everything remains the dimensional properties, and S is only the shear force acting on the section. So here the dimensions changing abruptly from this part. So this portion and this portion means at this level, so these two levels, suddenly the dimensions is changing abruptly. So we have to take care that part, and we have to divide the whole work in two parts. One is, first we will find out the shear stress distribution for this flange part separately, and then we will consider or calculate the shear stress distribution for this wave part. Okay, so if this is the I section, so first, what will be the neutral axis? As I told, it is the midpoint of the neutral axis. So here to here, what will be the distance? Here to here, what will be the distance?
Small d by 2.
Small d by 2. Good. Okay. Here to here?
Capital D by 2.
Capital D by 2. This is, we know, B. This portion we know, small b. So first we will think about this flange portion. So flange, the shear stress distribution for flange, that is this one. Let us consider this part as the EF level is so from this neutral axis, the EF level is y distance away and the EF level is situated inside the flange as we are trying to find out the shear stress for this flange portion. So what will be the shear stress in flange part? Can you tell me what is the, first write down the formulas. Then try to replace these components of this formula in terms of known parameters. So that will give us the shear stress. You can think of for some time. If you have any doubt why we have considered this EF there or anything or any related question, please ask. Huh? What is the shaded area of the flange? A. We have done it in similar for the rectangular part. Please go back and have a look.
So capital B into dy.
Capital B into
dy.
capital B into D by
D by 4. Capital D by 4.
capital D by 4. Okay. Anyone else? Is he right?
From neutral axis, capital D by 4 plus D by 2.
Okay. Okay. What we have done in the rectangular part? नोटबुक में तो होगा ना, एक बार देख लो. किसी का कोई दूसरा आंसर आ रहा है अबाउट दिस शेडेड एरिया ऑफ फ्लैंज? अभी तक जो आंसर्स आया है उससे उसके अलावा where this shaded part is situated, y distance away from the neutral axis.
So capital D by 2 minus y into B.
हाँ, तो because what is this height of this small portion of the shaded area? That is nothing but this total d by 2 from neutral axis minus this y, right? So let me withdraw some color part or anything. Yeah. So this height is t by 2 minus y. Why? Here to here is capital D by 2. Again here to here is y. So remaining क्या बच गया? D by 2 minus y. Into, as the area is within this flange and the width of the flange is b, so into b. Any doubt? किसको समझ में नहीं आया? If it is fine, then you can tell me the y bar also. Think about it. This shaded area is a rectangular portion, na? So where the center of gravity of a rectangular portion will lie?
Sir, y plus half d by 2 minus y.
Y plus half d minus 2y. Yes. So तुम प्लीज एक्सप्लेन कर दो कैसे तुमने समझा ये चीज.
सर मैथमेटिकली किया मैंने.
यस, थोड़ा बोल दो फिगर देख के, सो दैट एवरीवन आल्सो कैन अंडरस्टैंड.
सर पहले उसका वो डिस्टेंस निकालना है ना एन से.
एन से डिस्टेंस तो y है, और सेंट्रॉइड पोर्शन ऑफ द शेडेड एरिया तो बीच में होगा. कहाँ पे होगा?
सर बीच में होगा ना उसके.
यस, तो बीच में होगा मतलब कितना दूर पे चला जाएगा वो EF से?
EF से सर आधा डिस्टेंस होगा ना.
आधा डिस्टेंस. तो व्हाट विल बी द आधा डिस्टेंस? हाफ ऑफ दैट d by 2 minus y. तो अभी हम लोगों को चाहिए डिस्टेंस फ्रॉम Na, तो बीच में कितना एक्स्ट्रा गैप है? y.
यस सर.
सो y प्लस, सो y में वी हैव रीच्ड EF. देन EF से भी इसका सेंट्रॉइड पोर्शन पे जा रहा हो हम लोग. Don't think of it, it is a centroid portion. Okay, so that is nothing but half of this part, half of d by 2 minus y. What does it mean? D by 4 minus y by 2. Y है, so d by 4 plus y by 2. प्लीज आस्क मी इफ यू हैव एनी डाउट. ठीक है, अदरवाइज बाद में दिक्कत हो जाएगा. सो y bar is the distance of center gravity of the shaded area from neutral axis. It is summation of two distance because पहले तो neutral axis से we have reached EF, then EF to the center of gravity of the shaded part. So that's why y, then half of this part. Now this is coming as d by 4 plus y by 2. Now what will be the shear stress for this flange portion? Anyone?
Sir, s by 2y
Mm-hmm.
into d square by 4 minus y square.
Good. So what he has done, he has basically replaced this a and y bar with these expressions. So this tau equals to s into b into d by 2 minus y, that is the a part, and d by 4 plus y by 2, that is the y, that is this y bar part, into by I into b. Okay, so okay, interestingly, SB by I small b into half of d square minus 4 by y square, it is coming. So basically SB by 2IB into d square minus by 4 by y square. Okay, so here there are two b's. What was your answer? Who just said?
Sir, s by 2y.
तो तुमने बी को एक सेम सोचा और कैसे इसको नलिफाई किया?
सर सेम ही सोचा मैंने.
ना हुआ है?
सर सिमेट्री.
हाँ,
सिमेट्री का यूज करता मैं.
सिमेट्रिक के लिए सोचा सेम.
यस.
ओके, ये जो बी एंड स्मॉल कैपिटल बी एंड स्मॉल बी सेम होगा और अलग होगा. फॉर फ्लैंज what is the definition of small b?
सर सेक्शन की विड्थ होती है एफ लेवल पर.
सेक्शन का विड्थ होती है ईएफ लेवल पर, वो इंपॉर्टेंट है. सो सेक्शन विथ ईएफ लेवल where is EF level? Where is EF level?
Flange.
फ्लैंज पे. तो इस पे विड्थ कितना है?
Capital B.
कैपिटल बी. सो जो तुमने बोला कि सिमेट्रिक होगा, समझ में आया क्यों वी आर कैंसिलिंग आउट दिस टू? नॉट बिकॉज ऑफ द सिमेट्री, बिकॉज ऑफ दिस रीजन. सो
Yes, sir.
बेसिक, हाँ, अंडरस्टूड ना?
यस सर.
So here S by B by 2 into I, this B is the section with that EF level. As we are talking about flange and the EF level is within this flange, so here the width will be capital B. So that's why we will write it as capital B and the remaining portion will remain same. Then we will cancel it out and it will come up as S by 2y d by 4 minus y square. This is the shear stress for this flange portion, just this part, for this flange portion. So what will be the two extreme points of this flange part? So tau equals to S by 2i into d by 4 minus y square. So what will be the y value? What will be the two y values for this flange? How the y value will vary? Yes, please answer the
Sir, capital D by 2 say small d by 2 तक.
capital D by 2 small d by 2. Good. Because the y is from the neutral axis. Now at this portion means the junction of this flange and the wave, what is the value of y? Small d by 2. And at the top part of this flange, what is the y value? Capital D by 2. That means so here to here is d by 2 and here to here is capital D by 2, right? So the y can have maximum value of d by 2 and minimum value of maximum value of capital D by 2 and minimum value of small d by 2. So y for capital D by 2, what is the shear stress? Just put it here. We can have 0. Y for small d by 2, what will be the shear stress?
So S by 8I into D square minus small d square minus d square.
Yeah. S by 8I into capital D square minus small d square. This y equal to d by 2 means at upper edge of flange, and this y equal to d by 2 means at junction of wave and flange. Right now, this is the junction of this wave and flange. So this is S by 8I into capital D square minus small d square. So this is all happened for shear stress in flange. Now we will look for the shear stress calculation in wave.
सर I की क्या वैल्यू बनेगी इसमें?
बोलो बोलो बोलो
सर I की क्या वैल्यू बनेगी?
I का क्या वैल्यू होगा? I का वैल्यू एक्चुअली the I is the moment of inertia of the entire section. Okay, so entire section means ये जो complete I section है ना, इसका moment of inertia तुमको निकालना पड़ेगा with respect to the neutral axis. Because that's what we have also, because the formula says like what for the rectangular portion, what you have considered the I value? जाके एक बार देखो. What you have considered? The I?
So 1 by 12 BD cube.
BD cube by 12. अब उसमें डायमेंशंस क्या था? B टोटल width था, D टोटल हाइट था तो उसके लिए न्यूट्रल एक्सिस में BD3/12 यूज किया. What I value for circular section you have used again for the entire sections. So here also we are just dividing our job in two parts, but the methodology will remain same. So here the I, by definition, it is the moment of inertia of the complete I section, this I section with respect to neutral axis. Okay. So we are going for the wave part now. So what is the, so for this case, this is our neutral axis. Now for wave part, we will consider the EF level at within the wave and all the area above the EF level we have to consider. That is the definition. Ki EF level which is say y distance away from the neutral axis, we have to consider the total area above the EF layer which is y distance away from the neutral axis. So now we have to use this formula and we have to replace the components and then we have to rewrite the expression. So how we can do that? Most convenient way how we can do that? So first think about this flange part, this horizontal rectangular portion, then think about the small portion in the wave. So here it is flange, here it is wave. So first think about this flange part, okay, and everything about the neutral axis, then think about the small portion of in this the wave, and then we can add those parts. So let me divide this AY dash. If we want to calculate as FY flange plus AY y bar wave small portion. So what will be the AY for flange? The moment of area of this, the moment of radius of this area for the flange. This is nothing but area into the centroidal distance of the area from neutral axis. किसी का अगर हो जाएगा तो आंसर बोल देना. Anyone? What will be the area for the shaded part in flange? What is the area of the shaded part in flange?
So capital
Hmm.
capital B by 2 into D minus D.
Capital D by 2 minus B minus D. Okay, so can you tell me once area for the shaded part in flange? Please बोलो और एक बार.
So capital B by 2. So B.
Into B.
So capital B by 2.
अच्छा capital. Okay. Capital B by 2
Into D, capital D minus small d.
into capital D minus small d.
So area.
Okay. But I understand you have done it, but इससे ना काफी confusion आ जाएगा. That's why I was thinking, yes, you are right, but what the appropriate way to make it to write it is B into D by 2 minus D by 2, right? इसमें ना कोई confusion नहीं आएगा. It will be very clear. Yes, I understand कि तुमने वही बोला, but this B into this capital D by 2 minus this D by 2, because that gives us the height of this shaded part in flange. B is its width. That's why he told that this is the area for this portion. Now, what is the Y bar then for this shaded part of flange? So this will give us A.
D by 2, capital D by 2 minus y into
Yes, बोलो capital
capital D by 2 minus y
minus Y.
whole divided by 2
Okay,
plus y.
plus Y.
वैसा कुछ सर लग रहा है सर,
हाँ.
लग रहा है सर ऐसा है.
नहीं ठीक है, ट्राई ऑलवेज करना चाहिए, कोई दिक्कत नहीं है. सो what he told, everyone agrees with him or there is some other answer? We are talking about Y bar for the shaded area in flange.
So y की जगह small d by 2 आ जाएगा.
Y के जगह पे small d by 2 हो जाएगा, because the thing is that Y is not situated in the flange. तो जिसने बोला समझ में आया कि Y तो अभी वेब में है. So this portion we will consider entirely, na?
Yes sir, yes.
Yeah, right. So this small capital D by 2 minus, just 1 minute, D by 2 and
y नहीं होगा सर.
हाँ y नहीं होगा क्योंकि y is within wave. We are thinking about
Yes.
the flange.
Yes,
So
yes.
so capital D by 2 minus small d by 2 उसका बीच में आएगा हमारा centroid part. So centroid will be there, and from that the d by 2 is the distance and then the centroidal part. So here we will go first at d by 2 and then we will go the centroidal part. Okay, so that's how we are getting this. So cumulatively, what will be this ay bar for flange, the final expression, short expression?
So b by 8 into capital D square minus small d square.
Good. B by 8 into capital D square minus small d square. So this is the ay bar for flange. Okay. Now we will try to find out this ay bar for wave portion. Try to calculate. I am going in the next page. It's better to do it here. Okay. You can calculate. I am just rearranging this part. So now you are calculating the ay bar for the wave portion. The small portion wave, what is remaining in that at the between the junction of this flange and wave and EF.
Sir, BD square by 8.
Just 1 minute. AY bar wave you are telling how much?
Sir, BD square divided by 8.
B, कौन सा B?
Small b or
Small
d.
b and small d.
Yes, sir.
Okay, BD square
By 8.
by 8. और कुछ है और that's it. Okay, so BD square by 8 he said. Is he correct?
Minus by square by 2.
Minus by square by 2. Good actually. Who said this by square by 2? So how he has done it? Let me quickly do it with this color. So what is this A portion? What is the area of this portion?
So small d by 2 minus y into b.
Small d by 2 into y into capital B or small
b.
Small b. So this is the area. Okay. And what about this y bar?
So d by 4 plus y by 2.
Okay, we can little bit deassemble so that for everyone's understanding. So first we are going from neutral axis to EF Y. Then from EF to the junction, what is this part EF to junction is basic the centroidal is sorry not the junction sorry. So it is the centroidal portion of this part. So half of this portion, so half of d by 2 minus y. So if we see this a is like this and the y bar is like this, and then if you just, so this one basically is giving us d by 4 plus y by 2, and if we multiply these two, it is giving us a value of b by 2 into d square by 4 minus y square, as he rightly said. So if we just put this b by 8 here, it is d square by 4 minus y square. Everyone got it? How we can calculate this a y bar for wave? So now we have individually calculated this a y bar both for flange and wave. Now we will sum it up for this a y bar portion. So okay, it has come here. Just 1 minute. So now a y bar is basically a y bar flange plus a y bar wave. That means b by 8 d square minus d square plus b by 2 d square by 4 minus y square. So what will be the tau then? S a y by IB. Here we are talking about wave, shear stress in wave. Simply S by IB, just replace this one, B by 8 d square minus small d square so this is the tau for wave portion. Now the variable is only y. So what will be the two values of y for this wave portion?
So small d by 2 to 0.
Very good. Small d by 2 to 0. So y0 is giving us a tau equals to y0 means at neutral axis. So S by IB b by 8 into d square minus d square plus b d square by 8 because y becomes 0. So this is the tau max because y is decreasing the part. Now y becomes 0. So everything will be the intact and this is the maximum and this is at neutral axis because y becomes 0 at the neutral axis, and the other part he said that the y will vary from 0 to small d by 2. So what will be the shear stress at small d by 2? just this one. We are just replacing this y as small d by 2. So d square by 4, d square by 4, a aa jayega 0. So only this portion will remain. So s by ib into b by 8 small d square minus d square. So now let me write down, just a minute. Now let me write down all the part which we have calculated till now. So for flange and for wave. Okay, so one part is top of flange and second is junction of wave and flange. Okay, for wave, one portion is junction of wave and flange, and second is neutral axis, because these are the 2 points. Okay, can you tell me the values? We have already have calculated everything. Just give me the values now, give me the expressions.
So flange पे से top of the flange पे से 0 है.
0 है, okay.
So फिर से S divided by 8i into d square minus.
कहा किसका बोल रहे हो अभी?
So junction of web and flange पे.
From flange ना जो हम लोग डिसाइड किया, कितना आया?
So S divided by 8i into capital D square minus small d square.
Okay, good. Okay, now wave से क्या आया? Junction of wave and flange में?
So S divided by 8ib small b into capital B into D.
It's a capital B, okay.
Into D square minus small d square.
Okay. Or सेम है ना, जस्ट s by 8i into this one, अरे b by b को अलग कर दिया. ओके, और एक बचा हुआ है एट न्यूट्रल एक्सिस.
So S divided by 8ib
8ib
into b d square minus d square plus small b d square.
Okay, okay, thank you. So these are the 4 values we have calculated till now, the shear stress we are talking about. What is the interesting part? When we are calculating from flange portion, the junction of the wave and the flange is giving this value, whereas when we are calculating at the same portion from wave, this is giving same value but into some b by small b. That means at the junction of the wave and flange, the shear stress will suddenly jump off from this part, this portion to this one, because b by small b, here capital B is higher than small b, so it is greater than 1. So one value will be here and at the same point another value will be here. It is very similar like the shear force distribution याद है SFD and BMD जहां पे दो टाइप का वैल्यू आ रहा था, we are putting both the values and the sudden jump is happening. Similarly यहाँ पे भी shear stress का एक jump आएगा from this value, from the flange to the this value of this wave, and others are very similar. Similar means not so difficult. So this is basically tau max and this is basically tau min, right? Now if we want to draw the shear stress distribution, how it will be? Okay, you can just 1 minute. Okay. So now we want to draw the shear stress distribution. Before that, let me redraw. So this is the base of the distribution. Now here, let me write down the points. Okay, so this is the neutral axis. Neutral axis is having the maximum value. Okay, one more part. From the expression, this is again containing the y square part. That means again a quadratic function. So parabolic portion, that is for wave. For flange, also this is y square. So quadratic function, that means parabolic curve. Okay. So at the top of the flange, the value was 0. So it is here. At the junction of this wave and flange, from the flange, some value is here and which is having a jump off. So here it will have some value, and then at the same line, it will have some jump off. Okay, similarly, but because it is symmetrical, here it is 0, here some value will be there and it will jump off at the same point, that is junction. But at the neutral axis, it is having the maximum value. So at neutral axis, some maximum value will be there. So how we can connect this parabolic portion for this flange? This should be a little bit curvy. Yeah. Then it is jumping up at the same point. So straight line. And again, for the wave portion, y square is there. So what is this value here? S by 8b, this one. Because I am not writing, it is, you already have all these values. So here it is 0. Here it is the value of this one, s by 8i d square minus d square. So s by 8i into capital D square minus D square. What is the value of here? S by 8i D square minus D square into B by B, and this is the similar. So this is the shear stress distribution for symmetrical I section. Is that clear? Any doubt in the whole process? I hope कि सारे लिख लिया साथ में. अगर कोई दिक्कत है तो प्लीज पूछो. Okay, then we are going for the next part. Is basically, so this is a bending stress problem. Actually, I should not write this like way because in exam all questions will come together. So here an I section is shown. Please write down the this question. A simply supported beam is fine. What is that? I have to write, I have to draw this I section. Okay, I am drawing that, and you can first write the question and then draw the I section as I have drawn here. Okay, I have drawn the I section. You have to find the concentrated load acting on a simply supported beam. Okay. कुछ तो बोलो. Okay, I think we have given time. So इस टाइप का प्रॉब्लम हाउ यू शुड अप्रोच. An I section shown below is simply supported over a span of 12 meter. If the maximum permissible bending stress is 80 Newton per millimeter square, what concentrated load can be carried out at a distance of 4 meter from one support? So how a simply supported beam will look like? Can anyone tell? एसएफडी का चैप्टर में मैंने बीम का डेफिनेशंस ड्रॉ करके दिखाया था. जो क्लास नोट्स में उसमें भी सिंपली सपोर्टेड बीम कैसे दिखता है दिखाया था. हाउ इट विल लुक लाइक? एनीवन? अच्छा, लेट मी गिव यू ऑप्शंस. A, B, C, D. Which is simply supported?
C.
C. Okay. What is A?
Cantilever.
सर कैंटिलीवर बीम.
Yes. What is B?
Fixed beam.
Fixed. C is simply supported. And this is continuous. Okay, चलो definition हो. What this C? बोल रहा है कि concentrated load कैरी कर रहा है एट ए डिस्टेंस 4 मीटर फ्रॉम वन सपोर्ट. से दिस इज 4 मीटर. टोटल इज 12 मीटर. Say this load is say W, because we have to find out this W. What will be the steps from this? This is known to you, this part. What we should do? We know these forces, reactions. Acha, tell me what we have to do first in this problem. Simply supported definition, that is the fine. What we have to do? Can anyone tell me? एक बीम है जो सिंपली सपोर्टेड है, उस पे एक कॉन्सेंट्रेटेड लोड अप्लाई होगा एट 4 मीटर. ये तो दिया हुआ है, फाइन. व्हाट वी हैव टू डू और स्पेसिफिक, व्हिच इक्वेशन वी शुड यूज हियर? Which equation we should use here?
RA plus RB equals to W.
हाँ, और एक बार बोलो.
RA plus RB is equals to
हाँ.
W, and then
Okay.
moment वाली.
Moment about any force. Okay, no. That, yes, very good. I am coming to that. But before that, I am asking that which equation, जो last 2-3 हफ्ता में काफी सारा इक्वेशन डिराइव किया मैंने, उसमें कौन सा इक्वेशन यूज करूंगा इस पर्टिकुलर प्रॉब्लम के लिए? ये प्रॉब्लम किस चीज का है?
सर टी मैक्स और टी एवरेज के बीच का रिलेशन यूज करना है।
D max by T max and T average. Okay. Is it correct? Or we'll do something different? Okay. जिसने बोला अभी जो T max और T average का रिलेशनशिप यूज करना है, पहले तो है T नहीं, उसको टाउ बोलते हैं।
Yes,
टाउ,
sir,
हाँ,
टाउ।
टाउ का रिप्रेजेंटेशन क्या है? मतलब किस चीज का रिप्रेजेंटेशन टाउ है?
सर स्ट्रेस का, shear stress।
Okay, you are giving your answer only. So tau is shear stress. Shall we use here in this problem? यहाँ पे क्या स्ट्रेस दिया हुआ है?
सर बेंडिंग स्ट्रेस दिया है यहाँ पे।
बेंडिंग स्ट्रेस दिया हुआ है। बेंडिंग स्ट्रेस रिलेटेड कोई फॉर्मूला हम लोग किया है? It's not for him only. I am asking everyone. Anyone can answer. Because in exam ना, it will not be asked कि ये इस चीज का इस पर्टिकुलर फॉर्मूला यूज करो तो यू कैन सॉल्व।
जैसे क्या है फॉर्मूला?
क्या है? अच्छा, क्या इक्वेशन क्या है?
सर याद नहीं आ रहा उसमें।
इसीलिए मैंने कल लिख दिया था सारे इक्वेशन एक जगह पे रखो और क्लास के आने से पहले सारी इक्वेशन एक जगह रखो, सो दैट हेल्प होगा। और नहीं, ठीक है, आज भी नहीं किया, एटलीस्ट आज इस क्लास के बाद जितना भी इक्वेशंस पोस्ट मिड सेम मैंने डिराइव किया और जो भी दिया हुआ है सारे एक जगह पे लिख के रखो विद द चैप्टर नेम एटलीस्ट, सो दैट वहां से समझ में आएगा कि कौन सा इक्वेशन कहाँ पे यूज करना है। अदरवाइज वहां पे ऐसे नहीं आएगा कि इस पर्टिकुलर इक्वेशन यूज करो और फॉर्मूला कर दो। एनीवन कैन से, उसको तो याद नहीं आ रहा है, ठीक है, बाकी किसी को याद आ रहा है बेंडिंग स्ट्रेस रिलेटेड क्या फॉर्मूला हम लोग यूज किया?
नो सर।
ओके, किया कि नहीं किया? डिराइव किया ना ये वाला?
यस सर।
ये वाला किया?
Yes, sir.
व्हाट इज एम मैक्स?
Maximum bending moment.
व्हाट इज सिग्मा मैक्स?
बेंडिंग स्ट्रेस मैक्स।
मैक्सिमम बेंडिंग स्ट्रेस, because bending stress is denoted by sigma। सारे फर्स्ट चैप्टर में दिया हुआ है, स्ट्रेस चेंज चैप्टर में सबका रिप्रेजेंटेशन दिया हुआ है। अच्छा, व्हाट इज जेड?
सेक्शन मॉड्यूलस।
सेक्शन मॉड्यूलस, वेरी गुड। तो बस यही यूज करना है हम लोगों को ना, बिकॉज हम लोग ऑलरेडी ऐसे प्रॉब्लम किया हुआ है जिसपे शेप से रेक्टेंगुलर था। कॉपी में पीछे जाओ, ऑलरेडी वी हैव कैलकुलेटेड यूज, बट उस टाइम क्या था, जस्ट वी हैव formulated that formula and then we have used, so उस टाइम उतना कुछ डाउट नहीं आया था कि which formula to be used, right? Anyway, so this is the bending moment maximum, it is the maximum bending stress, it is the section modulus. तो जो ऐसे जो इसने बोली कि RA plus RB equal to W होगा and एक मोमेंट लेना पड़ेगा, तो किस लिए करेंगे हम लोग? Because we want to find out the maximum bending moment. जैसे ही वो मैक्सिमम बेंडिंग मोमेंट आ जाएगा वही हम लोग इस पे यूज करेंगे. मैक्सिमम बेंडिंग स्ट्रेस दिया हुआ है एंड व्हाट इज द सेक्शन मॉड्यूलस दैट वी विल कैलकुलेट फ्रॉम दिस आई सेक्शन. Any doubt? So that's why there are 3 parts, right? So, नहीं तो okay. So M max is sigma max into Z. Z is, what is Z? Section modulus. How we can find your section modulus? What is the formula for Z?
I upon R. I upon Y max.
Yeah. I upon Y max. Okay, good. ठीक है. अभी हम लोग के पास अच्छा पहले तो जैसे तो पहले हाउ वी कैन फाइंड आउट दिस एम मैक्स, क्विकली वी कैन से हाउ वी कैन फाइंड आउट दिस एम मैक्स. मैक्सिमम बेंडिंग मोमेंट, मैक्सिमम बेंडिंग मोमेंट कैसे आएगा? You have done it in the assignment, na? In assignment 3, one type of formula was given exactly like this. Okay, there is lots of time happened. Let me finish it quickly because you are also going for lunch. So this is A, this is B, this is 4 meter, this is 12 meter. So as she rightly said, this is RA, this is RB, RA plus RB will be W. That is one equation. Another equation, we are taking a moment about A. So RB into 12 equals to this 8 into, there's W into this 8, this portion. So 8W. So RB is basically 8 by, so 2W by 3. That means RA is basically W minus 2W by 3 is basically W by 3. Now you tell me the maximum bending moment. How we can calculate the maximum bending moment? What is the section kato, then this into that displacement, right? Okay. So maximum bending moment will come at this position. If you just find it out, you can see. So here it is RA into 8. Also, if we coming from this section, we can say that RB into 4, both the case it will give us the maximum bending moment of 8W by 3 Newton meter, because it is in Newton. Okay, all these things are in meter. So 8W by 3 Newton meter. Okay, and what is this Z? I by Y max. I for INA, right? So Z equals to INA by Y max. What will be the INA for this I section? I am writing the expression. Please class के बाद देख लेना. So this is the I. Y max will be nothing but this 225 by 2 equals to 1112.5 millimeter, and this is in millimeter to the power 4. So Z will be this INA by Y max, and M max is equals to 8W by 3. Sigma max is equals to 80 Newton per meter square, and so 8W by 3 equals to, okay, just 1 minute. This is in Newton, so 8000 W by 3, because this is in Newton meter, we have just converted Newton millimeter into this 80 Newton per millimeter square into this value. So not this one, is this Z, and from here W will be 8369.77 Newton. Okay, so this is the answer. Okay, this problem is already given in the example problem. The book I have shared with you. Please go back and check this point, check this problem. In fact, all the problems are from that book only. So you will find out this value of W. If you anyone so to understand this part, I can discuss, but at this moment, let me take your attendance, and then you can go, because